Okay. Should be on. I do like how this tends to send it very quickly. At least it shows that it's streaming.
Ironically, so it sounds better than the actual Zoom streaming part of it.
Yeah, it's like it just goes really fast. So let me make sure it's on here. Yep, there it is. So I can get rid of this now. Okay. So yay. Alright. We're live. Welcome into Space Weather Unplugged for this weekend's edition. We're going to talk filaments. We have a prop. We actually have a prop.
First prop ever.
First prop ever. You know, everybody knows the Slinky by now, but I figured, hey, we now have one. So we're going to talk filaments and streamer blowouts. I just like the name streamer blowouts.
It sounds so dramatic.
It does. It sounds very dramatic for something that's not really dramatic. I guess it is, but it just takes like...
It looks dramatic.
Yeah, it's like... I don't know. But anyway, we're going to talk about these two things because they can be sources of stealthy CMEs. Actually, some filaments are pretty, like, you know they're coming, but sometimes not. The streamer blowouts, though, tend to be very stealthy. So that's kind of a neat one to go into. But to start it off, we're going to talk current events. So, what do we got going on? You want to bring up the, Oh, wait, did we want to do it? We put it in the, slideshow, didn't we?
We did, but if,
I mean, I got the chronographs.
Yeah,
Yeah.
okay. We can probably pull the real-time solar wind.
Pull the real-time solar wind. Because we have wonderful steady magnetospheric convection conditions right now. Which means not a whole lot
Which
going
means, or I guess, yeah, in this case, it means, oh God, 27 years.
Yeah, you wanted to do 27 years. Here's 27 years worth of data.
I've been doing so much lately. Okay. So, as we've seen, there have been no filament arrivals, or sorry, no CME arrivals. We're talking filaments so much now, I keep saying filaments.
Yeah.
Which, I'll be honest, not very much of a surprise.
Yeah. We'll get to that in a second.
Oh, that's an interesting spike. I didn't notice that was there. First time really looking in detail over the last 24 hours.
Maybe that's our missing CME.
Let's see. That's in solar wind data and mag data, so it was definitely something. Don't really get to see those very often. That's probably not an anomaly. Anyway, point being, nothing. We are very steady, quiet, 3-4 nanotesla. We have very slow solar wind. We do have some consistent BZ going on now, -1, -2, so likely, what, Arctic SMC level or something close to that?
Yeah, we found one webcam in Sweden that's not clouded over that currently has aurora, so it's kind of typical for...
One webcam in Sweden.
Because everything else has clouds. So we found one clear-ish.
Oh, there we go.
That one. Right
Ta-da!
there.
Yay!
So there's your data. Here's the results of those data in the Arctic region. So if you're at high latitude, this would still give you aurora to look at. But, yeah, nothing too exciting. But in other words, like, we were expecting, I don't know what, 5 CMEs the last couple days?
I think we were up to 6 CMEs,
yeah, something
according
like
to
that.
some sources, but
if you here's the
I
video.
got one, and this is just that region, so I'm not really including the northern ones. 2, 3, 4, 5. There was 2 in there consistently, so at least 5. Yeah, but really, none of them. I wouldn't blink an eye out any of them. Really, they weren't even half halos. There was clearly not very much, if any, of an Earth-directed component, and they were weak at best.
Yeah,
looking at the dimming was especially not very interesting.
That was the thing that was because everybody was getting all excited about it, and the whole time we're like, I don't know, like everything just looked like it was pushed south.
Yeah, I did not make any posts because I'm just like, this is stupid. Like, let the hype talk. I'm gonna not say anything and be like, oh, I didn't know anything was coming because nothing clearly is coming.
But we had what was the other solar?
we did talk about it on Monday.
Yeah, we did.
That's true. Yeah.
Yeah,
we had that
not
one,
particularly thrilled.
and then one went off again while we were doing it.
Yeah.
Yep, pretty much just before we went on.
Yeah. So in case you're wondering, active regions typically, once they start firing, unless they drastically change, they typically will fire the same type of direction. So it's like a copy paste scenario almost. So the first one was pushed south. The subsequent ones follow the same sort of trajectory. So it wasn't super shocking, to say the least.
No.
No.
But, you know, it was the holidays. Everybody wanted some Christmas aurora. It was being hopeful.
We
Sorry,
got
nature
Christmas
said no.
clouds instead. Yes.
Yeah, we
Christmas
did have a lot of
clouds.
clouds, so, you know.
We did.
But anyway, oh yeah, I guess did we want to talk? Oh, we wanted to do the cautionary. I guess we'll bring up the slideshow because it's in the slideshow.
Yeah, let's do.
Yeah.
And let's do.
And then we can go to the
cautionary
video
tale.
once we get to that point.
Yeah. Okay.
Sure.
All right.
And again, just a quick reminder that all the modeling that M2M, NASA, and SWIPC with NOAA are doing, they are for different stakeholders. And that is a risk-based modeling. They need to know whether or not something major is coming so the industries can be warned and take appropriate actions. It is not meant for Aurora. As we can tell, sometimes they are wrong, and sometimes people who are looking at it who really probably don't have the right experience with looking at the data and modeling us
Yes.
may be right. Doesn't mean we're always going to be right. No, we will be wrong too. It's all the challenges of space weather, and this is how it goes sometimes. So not surprising at all.
Yeah, not at all. So,
Well said.
Can you see this? I was trying to do. Hold on, because I want to be able to see the OBS software as well as.
Oh, you're back to 2 screens, right?
Yeah, I'm back to 2 screens. So now I have to figure this out here. Okay. All right. So share. Okay. Let's do filaments and streamers. Okay. Well, I might have to deal with this. So okay, but you can see the slideshow, right? Maybe.
Yeah,
Yes.
I can probably. Let's see if I can. Slideshow. I can probably share if you want me to.
Okay.
Oh, there you go.
All right. I'll pass it over to you.
All right.
So that way I can still keep an eye on things.
Do the sharing. We kind of went over current events already, so we'll pass that on and go to Solar Orbiter, because Solar Orbiter is still close enough to Earth, so to some degree it can be used as advanced warning system, but it is getting to be pretty tricky. Currently it is at 12 degrees and probably going to separate even further, because you can see the future orbit is taking it away from Earth even sooner. So some of the events will register with Solar Orbiter and will not show up at Earth. And that exactly was the case recently. Something did bump the Solar Orbiter. Was fairly short-lived, so it lasted about, 12 hours or so? So this is relatively short for CME. It probably was a glancing blow from one of the events. Which one? We will never find out, because guess what? They don't come with a label. We keep asking for one, and they're still not labeled. So we are guessing
My
at
favorite
best.
complaint.
Yes.
I know.
Which one?
Customer service at L1, please label CMEs if you hear us.
Pretty
But
please.
unfortunately, it's our best guess. With the number of very small CMEs we've seen, if anybody wants to take a stab at what hit Solar Orbiter, we can open the lottery. And there is your guess is as good as ours. Plasma did arrive. It created some magnetic disturbance there. Solar Orbiter sent message to us, hey, something hit me. What it is, we don't know. Doesn't mean it's coming to Earth. Tough one. So it's wait and see. And because nothing was really Earth directed as far as we could tell based on dimming, and with a number of events, it's pretty much wait until something arrives at L1, and nothing came. So this was already a glancing blow. We can't really tell if it's flying from sort of more eastern or western direction at Solar Orbiter, but messages extrapolate with extreme caution at this point, because it is further and further apart, and it is getting to be fairly unreliable as an advanced warning system for us, particularly for very narrow CMEs. All right.
Amen.
Looks like a northeast-south flux rope, too. I just noticed that in there.
Okay. Thanks.
Not that that's relevant, but yeah.
Yeah. No,
I just noticed.
That was actually my assessment too. But again, it was very short and it went through pretty quickly and never arrived at Earth. So we're going to see more of those events that bump Solar Orbiter. It is coming back in March, actually. So it's going to be even closer to Sun than it is right now. and it will be a better resource for us as an advanced warning system, but we'll have to wait until March. So until then, use it with caution. So we're going to talk about solar structures that are above and beyond sort of, like, we're going to expand your mind as far as what sun can do in terms of structure. Solar wind is highly structured. We usually think for aurora about CMEs and co-rotating or stream interacting regions and high-speed streams, but there is a lot more that's going on with the sun that actually can have both appearance in a solar wind and impact on Earth. And we'll put that paper in reference because it ties all of it together very, very nicely. So if you want to dive deeper into solar wind, there is a paper for you. But we will talk about, well, we're going to be somewhere here on more of the mesoscale, which means medium size events, medium size structures. And again, CMEs, why are we talking about it? Because CMEs, we typically think about them coming from active regions, and that's probably the most common source, particularly during solar max. There are filaments, and that's going to be what we are covering today, and Hellman streamers, which are very interesting structures that we don't really get to see until solar eclipses, but we can actually see them with LASCO. So let's talk about what happens on what's called quiet sun. Quiet sun means it's the sun that doesn't have an active region, and it is actually quite active. So the whole idea of there is calm and nothing happening, that's just wrong. Because quiet sun is an area where the regions of opposite polarities, so negative and positive, they interact and they sort of touch each other. And when it happens, there are loops that are formed between regions of opposite polarity. If you think about the magnet and do a little bit of kind of magnetic iron dust, you start to see those lines that are forming. But sun is also a very active star, so it is producing tons of plasma. And that plasma, if Mary Beth, if you can show your rope, what happens if you have a loop of plasma and nope, without the twist. But if you start to
like a loop,
pull it, yeah, exactly. You start to pull it, you form a really, really long ray. Magnetically, it's going to be one side is pointing outward away from the sun, and the opposite side will be going back to the sun. So that's your coronal streamer, and you will see those structures during solar eclipses. It's sort of wispy rays that are coming off from the corona. There are other things that are happening there. So that's a region that's magnetically kind of sort of stable. So this is an area where you can see filaments. And those are big clouds of solar plasma, and they're not just clouds, they're kind of twisted ropes. But we will talk about it very shortly. They do form those prominences or filaments. So prominence is something you see on sort of the edge of the sun, and filament is something you see on the disk. Is it the same structure? Yes, it is. All right.
Yeah.
So, it's like a CIR and an SIR.
Yeah. Yeah, that's one of the
pretty much
one of the common questions, like the difference between a prominence and a filament, and they're the same thing. It's just where
angle.
The angle that we're looking at.
Angle of observation.
Prominences are fun to look at because if you are looking at the edge, you can see the structure better usually, especially
way more detail.
So they're just kind of fun.
So this is a solar minimum where you really have just a belt because you have clear separation of what's going towards the sun and away from the sun. And North Pole and South Pole magnetically, they will be fairly well separated with a kind of a line in between. For active sun, you have poles just about everywhere. You have regions of opposite polarities touching each other in many different locations, and it's all a mix. It's sort of like a lava lamp. And when you have the two liquids in the lava lamp that interface, that's where you're going to see that streamer forming. At least that happens on the sun. Not in the lava lamp, sadly, because that would be beautiful. All right. So what are filaments? And filaments are the same flux ropes. So they are ropes of magnetic field lines with trapped particles. So sun is made of plasma, and you have electrons and protons and all sorts of other particles that are flying around those magnetic field lines, and they're trapped. So they're stuck there.
Yeah.
And when they organize into more of a flux rope kind of twisty thing, and that forms because sun rotates unevenly around the equator and further out toward the poles, it's going to twist it into something like what Mary Beth has right
So I'm
now.
going to twist it up as best I can here, but you see, it starts to kink and turn into like an S, a sigmoid type shape, and that's where it'll get unstable and snap or reconnect, I guess you can say. But that's typically how you can tell when a filament is ready to go is when it twists enough that you start to see that kink, and then that'll make it unstable, because magnetic field they like to be in stable situations, not unstable ones. So they will try whatever they can to get back to those stable states. So that's where we get these eruptions from. But yeah, this is fun. There you go. There's the sigmoid.
Yay! Yep. So those flux ropes are colder. They're still hot, but they're colder compared to surrounding plasma, so they appear darker. They're also dense, and they keep on twisting. And sometimes they do twist to the point where you just twist them to beyond the point of stability, and they kink and they fly away. They do have a lot of supporting structures, so they're not just hanging out there all by themselves. There are loops of plasma over them. There are also sheared arcades that support the filament from underneath. That's at least one of the theories. So they're kind of on the magnetic cushion, and there is a magnetic barrier that lies over them, so they're not flying away on a whim. You can trigger eruption by having a solar flare next to that, because that's going to destabilize the entire structure, and lo and behold, the filament just flies away. Or by twisting further and further and further, just as Mary Beth was showing with the rope, you get a kink in it, you get it unstable, so it breaks off and just flies in different directions. And we have a few cases of that to show you.
Yeah.
So this is what happens over time. And this actually happened within a relatively short period of time, but there was a fairly stable filament that was laying there. Then it started to form a kink to the point where it had to reorganize and stabilize again. Again, those kinks are not very stable structures, and any system will try to reduce the instability and complexity, and how it's done is by sometimes eruptive events. You just tear it off and reform it
Right.
in a different way. You just don't need that kink anymore. There it goes.
Oh yeah, here's the
we
video
have
of
an
that.
example of that. And this is a filament eruption from September 16th of 2023. Off it goes. Those are very spectacular. Again,
Yeah.
there was a very dense filament that was laying there, and there was a flare that happened, and then filament just flew off. So that flare does not happen in the filament itself. The flare often happens in the active region that's next to it, but again, it's not a requirement. Some filaments just break off and go on their own. The bigger the filament, the higher the liftoff speed it needs to have. Otherwise, it's going to be reabsorbed and it's not going to leave the sun. How many filaments exactly make a CME as opposed to get reabsorbed? Well, the studies are anywhere from 10 to 90%. And when you take into account how fast they're leaving and how big they are, that starts to be a little bit more clear. So for shorter filaments, you don't need as much speed. You don't need to put as much energy compared to some of the long filaments. So that one probably took a lot to lift.
Yeah.
There we go. They are difficult to model. So when it comes to forecasting geomagnetic storms or CME arrival from filaments, they tend to travel slower compared to flare-related CMEs from active regions. They're very dense. They do pack a punch when they do arrive, but they might be coming on a later time. But it depends when they encounter in the space traffic, so to speak, in the solar wind. There's also a lot of twist with eruption, so there is rotation and deflections are fairly common. So misses are possible, and some of the filaments that are kind of flying what seems like away from Sun-Earth line, they might result in a hit.
Yeah,
So those are notoriously more difficult to model compared to active region CMEs. And they can definitely cause some decent storming.
yeah. The density of them is just kind of what drives that, because like we were saying, a lot of times the speeds are slower, but the density is quite high, and then like, you can get some really good geomagnetic storming from that. So
Not just from the density.
yeah,
So density itself is kind of interesting. Everybody looks at density as sort of recognition of a big structure. But they do have a fairly strong magnetic field that
mm,
comes with it. So if we have favorable magnetic field, meaning it's BZ south or negative, you can get very decent storing from them. Density is sort of, yep, that's a filament, it's dense, but then it all depends on what magnetic field it carries with it. And again, it's been twisting and it can get pretty strong. And it can pile up things in front of it too, just like any regular CME.
I will say filament CMEs are generally the ones we do not expect structure for. So almost every time there's any sort of filament, you don't really pick out flux ropes. You don't really see constant periods, or you can, but it's really more unpredictable than the general CME. You can expect it to hit hard and probably last longer, but there's not going to be any real way to predict its orientation ahead of time, or even its constant orientation during it. So you're basically just waiting at L1 to see what happens.
yeah. I think the best. I think we have that example in here though, somewhere. Well, this is the
That's what we have. So I think
yeah.
Christian, it's your, if you want to show
Yep.
this.
So this was the famous filaments of August of 2012, and I was able to lucky enough to watch this one happen as it did. Oh, we don't need the let's
I
go.
think anybody watching will recognize this because it's been used
There are
all over the place.
multiple photos of this one being used, and I do mean multiple. Now just give the there we go.
It's
Time
pretty
to adjust.
spectacular.
So this was a filament in the southeastern hemisphere during solar max of cycle 24. This was the northern hemisphere's peak. So usually there was a bunch of stuff going on there, but this filament was here, and you see this in wallpapers and everywhere because of just how photogenic it was. So I'm going to shut up and let it go, but let's see. Let's do 35 frames per second to really make the point. So that's this filament here. Just watch as it twists and starts to lift, and how brilliant it was. Like, I would have loved a wider angle on that one, just to see how far out. And I'm gonna let it go one more time because of how amazing it was.
Yeah, it's a pretty one. It just is.
And so what you normally see from the photos of any sort of well, NASA mostly uses this a lot, or SDO sometimes, but there's the stretching part here. And you will see this in documentaries. Anytime the sun is brought up, it's just, oh, this is the sun, even if it's not relevant to, they're not studying filaments. This is what is usually displayed now. So if you see anything about the sun and exploding, or even just an active sun, it's almost always this clip now. And then we have the actually here, I'll go back to whoever was sharing the slideshow because we got the data there.
Is this the
But we
most
did
exciting
receive
thing that came out of Cycle 24?
it was the top 3, easy. Yes. The other top 2s were well, the active region, I think 1429 we had in 2017, and then March of 2012 was a pretty good one too. There was a nice, no, that was 1429. March of 2012 we had just a 3 or 4 different X-class flares that were really pretty looking.
Oh.
But point being, this is the solar wind data we had once that filament arrived. It was an asymmetric full halo, so it hit Earth. It was not the central aim of it though, so we didn't get hit by everything, and we still saw BT levels of about 24, 25 nanotesla that lasted 12 to 20 hours before it finally calmed down. There were some negative periods of BZ. This was not a consistent as far as, or even in depth. 10, I'd say, minus 10, and except for the very beginning, we saw minus 20-ish, but that was only about a half hour. It did give us G2 storming, a couple different periods, though. So it was a fairly good aurora show for the time period. And again, cycle 24 was boring in general, so this was a pretty big deal when it happened. And then looking at TGO we have over here, it was a pretty constant. Check out that central just bump up as soon as the filament hit, and then
Right
some
there.
decent geomagnetic storming after that. Not very
Yeah.
much, but it was
Not very
there.
much, but considering this was morning arrival and it still resulted in
Yeah,
some
these are
decent
morning mags.
storming
That's true.
Mm-hmm.
for Canada, so I can only imagine how good it must have been for Tasmania and New Zealand. So they lucked out on this one. This is 200 nanotesla scale. So what you're looking here at what seem to be fairly minor things, they're not minor at all. They're pretty significant deflections, but that's that's a magnetometer spoon. All right. And we also have coronal streamers that can erupt and produce CME. So remember, those are the loops that connect sectors of opposite polarity. And right
Loopies.
now, this is more recent Lasco frames. So this is a coronal streamer. It has that structure, kind of a little bit of brightening here, and those wispy rays that are spreading out further and ending actually very, very far away from Earth. They extend very far, um, pretty much all the way to the heliopause. So they're pretty much ubiquitous in um, interplanetary space. Um, they are sources of mostly medium to small scale solar wind structures. They form blobs, and they may be a source of CME. So Sun has an interesting way to deal with those twisting. If it doesn't like something, it's just going to toss it probably toward more of a coronal streamer because that's the area of opposite polarity and fairly stable all by itself. But again, it has an interface in differential rotation. So something may actually erupt and either form within the streamer itself or just float toward the streamer and form somewhere higher in the corona. Um, this is where those blowout CMEs can happen.
We got an
And
example.
this is a fairly recent example. This is from December 10th. We had a
Boy, that's a
beautiful,
perfect one.
very
Mm-hmm.
long-lasting streamer blowout event. What you see in them, typically it's gradual swelling over several hours. That streamer gets wider and brighter, and then it erupts with a typical CME structure because there is a flux rope in it. They form higher in the corona. They're not low to the surface of the sun. They're very high up, and unfortunately, they do not cause dimming. They
Right.
are harder to pick out if they're kind of staring right at you. We end up missing them, and they form those stealth CMEs. We can see that there is a CME because it will form a halo, but it really depends just how much material is there. And sometimes we may miss them depending on what Lasco was doing at the time, but they don't have a clear on-disk signature. So you're looking at it and you don't know where that eruption came from, and you may assume it was farsighted when it really wasn't. Some of the modern methods of detection may pick them up, so we're getting better at picking them up. They're still very easily missed, and they may arrive like we actually have seen recently on I think December 17th was sort of unexpected arrival of fairly strong CME. Where it came from, there was nothing forecasted at the time. That clearly was not the CME we were waiting for. But it came out of nowhere, so it may have been one of those stealth CMEs. They are the CMEs, those streamer blowout CMEs happen during solar minimum because we have a beautiful streamer belt that's
Mm-hmm.
kind of that's sitting all over the equator of the sun. And if sun has that magnetic kink that just needs to be get rid of, needs to fly, it may send it flying toward us. So
Yeah. No, these are neat. And the other thing is like they're very slow. Like what is it? So what's the average in that paper? Was like 40
they are
hours?
actually going with the speed of solar
Yeah.
wind. So 400, 300, not unusual. They're not fast movers.
Yeah. So they can be,
And
like I said, they're just hard. They can be easily missed. But yeah, they're interesting. They're fun to look at when you can find them in the Lasco imagery. but
Yeah.
kind of an added annoyance to anybody that's got to do forecasting.
Yep. You can see them from the side. You can see
Yeah.
that swelling of the streamer, and then you see CME flying. But when it's flying, it's not flying in our direction.
Right.
It's
Yeah.
flying off to the side. And what's flying in our direction, we can't easily see.
So yeah, that's the other
That's a
fun
pain.
one. Stealthy.
Yep. Stealth CME. No clear on disk signature. So we know there is a CME. It might be flying our direction, but we just can't see where it started on the disk. It's happening very high in the corona, and that's why we miss it.
The worst.
So, yeah, it is. So all solar wind originates in sun's corona. Some of the structures may develop higher in the corona, will be harder to detect. Those are the CME blowout events. But the solar wind doesn't stop there. It actually evolves in transit to Earth, and some of the structures may actually form as solar wind is flying toward us.
I
So
know,
that's
crazy,
sort of
right?
that's sort of a preview of what we're going to be talking about within
Yes.
future streams.
Yeah.
So we're going to be talking about the solar wind when it actually comes our way. We do need more observations because we are starting to see evolution of solar wind thanks to Parker's probe and to Solar Orbiter. We found out that some of the flux rope erosion happens on the way from the sun to Earth thanks to Parker probe. We were thinking, well, the scientists were considering that solar wind and the magnetic field that it carries doesn't just sit idle and gets carried over to us. It probably does interact in transit, so Parker probe actually confirmed it. We do need more observations. And that will improve forecasting because right now models presume that nothing changes once CME is launched or once the solar wind leaves the sun, there are no interactions. That's not what actually happens, and that limits our ability to forecast things with greater precision and greater accuracy. So this is most up-to-date shot of the sun. And so from Solar Orbiter, it's kind of peaking from a little bit farther to the east. So
Yeah.
it's peaking behind the east limb of the sun. And we can see that there are a couple of active regions that are coming. Probably we're going to see them better in the next couple of days once they do rotate on the visible disk. But that's where Solar Orbiter is helpful. It will tell us what's coming when it's off the sun-Earth line, and that tells you what the value is in those multi-point observations. We can see sun from all the different sides, and that really helps.
Yeah.
So,
since we mentioned Parker Space Probe, it just broke a record.
Did it?
A couple
Yeah,
days ago.
I was actually good.
Fastest human object ever made, and that's closest ever to the sun.
Well, that's pretty cool.
Mm-hmm.
Yeah, because it made its closest pass, right? That's what I
Yep,
heard.
sure
it
did.
did.
Yeah.
For now.
Yeah.
So all the data from Parker Solar Probe will be used to model solar wind, and actually, hopefully we'll find out more. It really would help forecasting to know how it evolves from sun all the way to Earth.
Yeah, absolutely. Because I know a lot of these little things that we're kind of alluding to, a lot of it's really just theory, like, because we just don't have too much to go off of. So these two probes are really important because it helps verify things and further our forecasting abilities. So we like them.
I mean, let's just look at the most amazing too. We threw an object into the sun and it survived because it's
right?
swinging back around, so we missed a little bit, but we have an object going into the sun's corona and coming out intact.
That's pretty amazing, to be honest. I think, wasn't there a span of a couple days where they weren't going to have contact with it?
Mm-hmm.
Yep.
I could imagine
we just ended that as of now.
Just imagine being on that team and you're just sitting there like, well, let's just hope.
I should be receiving it around this time.
Yep, it was December 27th when it emerged. So
right, yeah.
We finally got the signal and everybody was excited, but I think it was as close as under 4 million miles.
That's
For scale, that L1 is sitting at 1 million.
yeah, that's close.
That's pretty close.
Yeah.
And it's very hot out there. So
Kudos to that team.
absolutely
They
for
built a great
thermal
machine.
yeah, we're building a great object that actually can
3.8
survive
million
that.
miles from the solar
Ugh.
surface. There we go.
Wow, amazing. Go Parker Solar Probe.
Right.
Yeah, absolutely. Well, I think that was what we had for today, right? That was our little preview.
Yep.
So yeah, I think we'll start with the beast of the solar wind structures for the next one. So that means we'll get we'll get into flux ropes and things like that too. That's kind of our little we sort of have a method to this madness, kinda. So just
Things just tumble into each other.
yeah, this is like the trajectory. So I know people have asked about the flux rope stuff, so we'll be getting to that shortly. But for now, hope you enjoyed the little primer into filaments and streamer blowouts because they are pretty fascinating. Filaments specifically, because we've actually had a lot of really good geomagnetic storms from filaments this past
Quite a
couple
few.
years. In fact, like the one April 23rd of last year, I mean, that was like the textbook example of a filament eruption and one that we actually had a clear flux rope signature on. But that typically doesn't happen, so it's nice when it does. But yeah, so hopefully you guys got something out of this, and if not, well, just ask us questions. There's actually, these papers are pretty involved, and we could have dived way deeper into this too, but it starts to get complicated really fast. And it's something that we could, leapfrog on too in the future.
Yeah.
Take it a little bit deeper. But we'll get there. So anyway, glad to have you here. Yeah, I don't know if you have anything to add, guys.
I'm good. That was
Okay.
a good session at this point.
Yeah, thanks Tanya for she's really good at explaining all this stuff. Like
Streamers were new structures
Yeah.
to really study for me.
yeah, so it was neat. It was neat to read about, and these other little things that happen in the solar wind too, because we come across this all the time. We're like, well, what was that, or what was this, and then you come to realize, oh, that could have actually evolved on the way here, which is just kind of like, oh, well, this adds a whole nother level of complexity to all this trying to forecast stuff. So it just gets more and more. The more you think you know about it, the more you don't know about it, and it's fun.
It's very humbling, that's for sure.
It really is.
Absolutely.
So on that note, we'll leave you guys. We'll give your evening back, and then we'll discuss what we'll talk about next week, which will probably be those solar wind structures. So anyway,
Woohoo!
have a wonderful night, guys.
See everybody. Happy New Year.
Yeah,
Bye.
Happy New Year.
See you next year.
Oh yeah,
Literally.
Yeah, see you next year.